In this video, we're going to talk about a mathematical concept, the concept of vector fields. This is maths, not physics, but vector fields are so crucial in so many areas of physics, particularly electromagnetism, that we're going to take quite a bit of time talking about the maths of these things. So what is a vector field? Well, as you can see, it's got two parts, field and vector. What is a field? Well, a field is something that fills all of space. The simplest types of field are so-called scalar fields. A scalar is just a number, like 4. So a scalar field is numbers that fill all of space. An example is pressure. Let's say you're under the ocean. At every given point, we've got the sea along here. At every given point, say down here, there's a pressure, and down there, there's a pressure, and over here, there's a pressure. So a scalar field would be some equation which would tell you what the pressure is at any given point. In the case of being under the sea, it just depends on how deep you are, so it's pretty simple. So a scalar field will be an equation or a table or something like that which tells you the value of a number everywhere. Perhaps the most important example of a scalar field in physics is the wave function, which is used in quantum mechanics. This is actually a complex number at every given location, so you need two parts, the real and the imaginary part, and that is fundamental to all quantum mechanics and indeed most of physics. So that's an example of a scalar field, but now we're going to talk about vector fields, as these are the ones that are most important to electromagnetism. So what is a vector field? Well, a vector field is simply an equation or a table or something that defines a vector at every point in space. So if I tell you a location, just to the right of my earlobe, you should be able to work out a vector there. So examples of this include gravity, the gravitational field. So let's say, for example, we have a black hole here. We should be able to define the gravitational field at any point in space. So for example, let's say the point we choose is here. It's going to be a vector pointing in that direction. If we're over here, we're further away from the black hole, so it'll be a shorter vector going in this direction, whereas over here, it'll be a very big vector going in that direction. So, the gravitational field, there must be some equation which tells you for any given point in space a direction and a magnitude, or if you prefer, an x, y, and a z component. How do you actually measure the gravitational field? Well, what you do is you take a little bit of mass somewhere and see what the force on it is, which way it accelerates. And that's in general how you measure any sort of field. You put something in a given place and see what happens to it, and that tells you the field. Another example of a vector field is the electric field. So if you have a positive charge, the electric field is going to point away from it. When you're close, it's going to point away very strongly. When you're further away, it's going to be a bit weaker. Further still, it's going to be smaller still, but it always points away. If it's a negative charge, it's reversed. And there's a magnetic field, which is a bit more complicated. In this case, if you have a wire with a current going down it, you get a magnetic field that curves around it. And there are more. You could look, for example, at fluid flow as a vector field. So let's say, for example, we have a building and the wind is blowing over it. So we've got the wind coming in here. The wind has direction. As it comes closer to the building, it'll move. Maybe you get an eddy going around there, some turbulence. So once again, at every point in the atmosphere, you have a direction and an amplitude. So that is another example of a vector field.